summations. See, if you look at on the board, sum of first and natural numbers is generally sum of first and natural is numbers is like this 1 plus 2 plus 3 plus and so on, and whose formula or whose summation is mentioned as n plus 1 by 2. And whereas the sum of first n even naturals, see the even number is usually of the form 2n, so all these numbers are in the form of 2n. Since I mentioned you n even naturals, the summation contains all these terms and its sum is given as n into n plus 1, right? And whereas the sum of first n odd natural numbers, see odd natural number is usually of the form 2n minus 1, so the sum of those terms is n square. Whereas the sum of the squares of the first n naturals, if you look at this squares of first n naturals, so you need to square the naturals, first n naturals, and the summation is n plus 1 to n plus 1 by 6. And now I am going to find the sum of the cubes of first n naturals here, right? We don't have the rule to find the sum of the cubes of first n naturals, and I am going to derive it now on the board, right? Just have a look at all these things. You need to pay an attention on the word first, right? I already mentioned you. See, all these formulas are applicable only if you consider the naturals or even naturals or odd naturals or squares, everything only if the summation starts at the number 1 only, right? See, have a look at all these things, and I am going to start. I am going to find the sum of the cubes of the first n naturals, right? See, already we find the sum of the squares of first n naturals as n plus 1 to n plus 1 by 6, right? Is it clear? See, that in the sense we have a procedure, we have a way to find the sum of the squares of the first n naturals. By the same way, with the same procedure, we are able to find the sum of the cubes of first n naturals, similarly sum of the fourth powers, sum of the fifth powers, and everything. But in most of the cases, in 99% of the cases, generally we face sum of the naturals, sum of the squares, as well as sum of the cubes. So that's enough if you know about the sum of the cubes of first n naturals, and that's enough for the class, right? Just have a look at this. I am going to find the sum of the cubes of first n naturals. I am again repeating the same process as we did in the did it for the sum of the squares, right? If you have any confusion regarding the way to find the sum of the squares of the first n naturals, now see, pay some more attention on the way to finding sum of the cubes of first n naturals. This way automatically resolves your doubts in that procedure also, right? Just have a look at this. Now what I am going to do, I am going to find the sum of the cubes of the first n naturals. That in the sense I need to find 1 cube plus 2 cube plus 3 cube plus and so on plus n cube. This summation value I need to find, right? As I mentioned you, to find this summation, initially you need to start with an identity. Identity means a mathematical equation which is true for all the values of the variable. That means that's mathematical equation is true at any time and everywhere, and in all the situations that is true for all the values, right? See, to find the sum of the squares, in yesterday's class we considered an identity that something you may say it as some k plus 1 cube, right? To find the sum of the squares, we consider the identity as k plus 1 cube minus k cube is equals to 3k square plus 3k plus 1. Have a look at this. You just replace any value in the place of k. Both left side and right side are in balancing position. Both are in a balanced way if you place any value in the place of k. So that's why we call these type of mathematical equations are as identities, right? So which is true for all the values in all the situations, right? See, to find the sum of the squares, we are considering this identity. But now my task is to find the sum of the cubes of first n naturals. Now to find the sum of the cubes, I need to start with another identity, right? See, we know that, right, it's a general task. We know that some k plus 1, have a look at this, k plus 1 to the power 4 minus k power 4. See, for squares we are considering the k plus 1 cube minus k cube. Now for cubes we are considering the k plus 1 power 4 minus k power 4. If they ask you to find sum of the fourth powers of the naturals, you need to start with k plus 1 to the power 5 minus k power 5. Now have a look at this. What is k plus 1 power 4? Already you know different formulas like k plus 1 whole square as k square plus 2k plus 1 and k plus 1 whole cube as k cube plus 3k square plus 3k plus 1. These two are the usually frequently used formula. That's why you are aware about those formulas. But k plus 1 whole power 4 is somewhat typical. Very rarely we use, right? See, k plus 1 whole square is nothing but the product of k plus 1 square with k plus 1 square. I think you are able to find k plus 1 whole power 4, right? See, you don't have in your memory, but it is possible to find, right? So if you find that k plus 1 power 4, which is nothing but k plus 1, k plus 1, k plus 1, k plus 1, multiplication of k plus 1 for 4 times. If you did it like this, and that k plus 1 whole power 4 is usually of this format, right? K plus k power 4 plus 4, k cube plus 6, k square plus 4, k plus 1. This is usually k plus 1 power 4 and minus k power 4 I am considering, right? See, this is usually k plus 1 power 4 actually. What I am going to tell you is this is k plus 1 power 4. But I need to consider that k plus 1 whole power 4 minus k power 4. So send this k power 4 this side. Then it becomes like 4k cube plus 6k square plus 4k plus 1. Right? This k plus 1 whole power 4 is a universal acceptable identity, right? So everywhere at any time for all the values that is true. From that identity, using that identity, I am going to find the sum of the cubes of first and naturals. Now have a look at this identity. This is like this. Now to find the sum of the cubes, you just replace k is equals to 1. If you replace k is equals to 1, how it becomes? I am rewriting here like this. 2 power 4 minus 1 power 4. Replace k with 1. Is it right? This is equals to 4 times of 1 cube plus 6 times of 1 square plus 4 times of 1 plus 1. Clear? Replacing k with 1. Since that is an identity, true for all the values, we have a chance to take any value. So to find this, my idea is replacing 1 to n all the naturals in the place of k 1 by 1. So first I replaced k with 1 and now I am replacing k with 2. If you replace k with 2, what will happen? 2 plus 1 is 3 power 4 and this is k 2 power 4 is equals to 4 times of 2 cube plus 6 times of 2 square plus 4 times of 2 plus 1. Right? See, concentrate here what is going on the board and replace k with 3. If you replace k with 3, k plus 1 is 4 power 4 minus 3 power 4 is 4 times of 3 cube plus 6 times of 3 square plus 4 times of 3 plus 1. So replace 1, 2, 3, 1 by 1 in the place of k. If you continue like this, at the end if you replace k with n, what will happen? If you replace k with 1, see this k plus 1 is nothing but n plus 1 to the power 4 minus n power 4 is equals to 4 times of k with n cube plus 6 times of k with n square plus 4 times of k with n 4n plus 1. Have a look at this. So now I have for k is equals to 1, for k is equals to 2, for k is equals to 3 and for k is equals to n. So totally how many equations I have? If you count, there are n equations like this. Now my task is add all these equations. While adding all these equations, have a look at the right hand side as well as left hand side alternately. Now if you look at the left hand side, and here this is 2 power 4 minus 1 power 4, 3 power 4 minus 2 power 4, like this it is there. If you look, if you are going to add all these things, yeah, what will happen? This plus 2 power 4 minus 2 power 4 get cancelled. This plus 3 power 4 minus 3 power 4 get cancelled. This plus 4 power 4 and minus 4 power 4 of the next term get cancelled. Like this n power 4s also get cancelled, and you left with this n plus 1 power 4 and that 1 power 4. Now you have in your hands that n plus 1 power 4 minus 1 power 4. Just have a concentrated look here. This is n plus 1 power 4 minus 1 power 4. Now just have a look at the right hand side. Now just concentrate on this first column. See 4 1 cube, 4 2 cube, 4 3 cube and 4 n cube. So you have a chance to common out the 4, right? 4 times of what you have in this bracket. See, this bracket contains 1 cube, 2 cube, 3 cube and so on n cube. That's what we need to find actually. That is our question mark actually. See, I am rewriting this question mark value as usually s, right? So that s is nothing but the required sum in this problem, which is the sum of the cubes of the first n natural numbers. I think it is clear. Now if you look at the second column, see, if you look at this second column, and this is 6 into 1 square, 6 into 2 square, 6 into 3 square and so on, 6 times of the n square. So if you common out 6, what is there in this bracket? See, have a look at this second column, right? 6 1 square, 6 2 square, we are adding all these numbers, n numbers, common out 6, then it becomes like how? 1 square plus 2 square plus and so on plus n square. Plus, now look at this third column. In this third column, 4 is the common number for all the n values. So just you common out that 4, and along with this 4 we have 1, 2, 3 and so on n. So you just write 1 plus 2 plus 3 plus and so on n. Plus, now you need to add ones. 1 plus 1 is 2, plus 1 is 3, plus 1 is 4. Likewise, if you add for n times, the summation is n. Now just have a look at this. Now, if you simplify this final result, this final statement by using the left hand side and right hand side, you get the value of s, and that s is the required sum, which is the sum of the cubes of the first n naturals. I will give you that sum, I will find it for you. Just have a look at this and I will find it. Just have a look at the problem. See, we are going to find the sum of the cubes of the first n naturals. If you observe, see, 1 cube, 2 cube, 3 cube, all these things are not an arithmetic sequence actually. But see, in finding the sum of the cubes of the first n naturals with this standard procedure, we are utilizing different formulas related to the arithmetic sequence. That's why usually we mention the sum of the squares of the first n naturals as well as the sum of the cubes of the first n naturals at this position after the summations of arithmetic sequence, right? That's why we also mention here, we are going to learn the way to calculate the sum of the squares as well as the sum of the cubes. Already we know, we found the sum of the squares, and now way of finding sum of the cubes is there on the board. Just have a look at this once again. See, we are finding what? Sum of the what? Cubes of the first n naturals. For that, I am starting with this standard identity. That identity is nothing but what? K plus 1 to the power 4 is equals to k power 4 plus 4k cube plus 6k square plus 4k plus 1. This is a standard formula for the k plus 1 whole power 4. I think already you know k plus 1 whole square and k plus 1 whole cube formula. In similar fashion, you are able to find that k plus 1 whole power 4 also, right? And I am using that k plus 1 whole power 4 here. Now if you send that k power 4 to the left side, it becomes like this. Now, to find the summation, we need to replace all the natural numbers starting from 1 to n one by one in the place of k for this identity. Now if you replace k with 1, you will get this first relation. If k is equals to 2, we have the second relation. If k is equals to 3, we have the third relation. Like that, you need to replace, see, 1 to n in the place of k for all this. And after that, you need to add everything. If you add, what will happen? See, in the left hand side, 2 power 4 minus 2 power 4 get cancelled, 3 power 4 get cancelled, and n power 4 get cancelled. You left with n plus 1 power 4 minus 1 power 4 in the left side. Whereas, coming to the right side, from the first column, common out 4 because 4 is there in every number. So, the sum of the remaining n numbers is the required sum. And for the second column, 6 is the common number, just pick it out. And then if you add the squares, this is the sum of the squares what we already found. And coming to the third column, 4 is the common number, pick it out. Then you left with the sum of the first n naturals. And already we have a rule to find the sum of the first n naturals, and we know that formula. Whereas at the last column, 1 is there in every relation. See, since there are n relations, we are going to add 1s for n times. Since you are adding 1s for n times, automatically the summation is n. So here we have that n. Now, by replacing this sum of the first n naturals, as we know it as n into n plus 1 by 2, and sum of the squares, as we know it as n in plus 1 to n plus 1 by 6. After that, you need to simplify for s. Automatically, you will get s. For the space concern, I need to erase something, but have a look at this. I will do here. Yeah. See, after this, what we need to do? Just look at this. N plus 1 to the power 4 again. See, this is n actually, right? Again, you need to concentrate n plus 1 to the power, n plus 1 to the power 4 minus 1 power 4. See, I mentioned you here k plus 1 to the power 4, But if it is n plus 1 to the power 4, what will happen? Everything is there in terms of n, right? So n plus 1 to the power 4 is the same relation with n minus 1 power 4 is 1. So you need to remove 1. Then you have that n power 4 plus 4n cube plus 6n square plus 4n is equals to, see, this is 4 times of s. That s is the required sum what we are going to find. 4 times of s plus 6 into this sum of the squares is nothing but n plus 1, 2n plus 1 divided by 6 plus 4 times of the sum of the first n naturals, n plus 1 divided by 2 plus n, right? That's what we need to simplify. Now this 2 2's, is it right? And then this 6 and that 6 will get cancelled. Now in the right side, you just leave that left side. In the right side, if you simplify, 4 times of s plus, see, n plus 1, 2n plus 1. If you multiply, what will happen? Have a look at this. See, you first of all multiply these two terms and then with n only. n 2n square into n 2n cube. And then n once is n, 2n, and then n is 2n square. And then 1 into 1 is 1, with n it is n. See, the product of these three terms is this 2n cube plus 2n square plus n, right? See, you just don't follow my simplification because it is completely algebraic simplification. See, you have your own way of style. Just go with that and then find that s. Plus now this 2 times 2, 2n plus 1. n square into 2 is 2n square plus n into 2 is 2n plus already we have one more n here. Now if you look at this, see, this n power 4 plus 4n cube plus 6n square plus 4n is equals to 4 times of s plus 2n cube plus 2n square plus n plus 2n square plus 2n plus n. Send everything aside. See, if you send everything to one side, how it becomes? I am rewriting here. Then just have a look at this. 4s is equals to, see, make this 4s as subject and send everything to one side. N power 4 still remains there, plus here it is 4n cube and there it is 2n cube. If you send this side, it becomes like 2n cube. And have a look at this. See, concentrate here. This is 6n square. See, in the left side. But where in the right side it is 2n square plus 2n square, 4n square. Send that side. It becomes like 2n square. Now again have a look at this. This is 4n in the left side and this is n, 2n, n. Again 4n in the right side. Both will get cancelled. So you have this as your final value. 4s is equals to n power 4 plus 2n cube plus n square, 2n square. Now if you look at this, n square, n cube, n power 4. N square is the common thing. Is it right? See, you have a chance to pick out that n square. And after picking out that n square, still you left with more n square and 2n plus what it is? 2. Is it right? Just have a look at this. See, is it right? Here I did some mistake there, right? n and then 2n, 3n, and this is 3n square actually. This is 3n square and this is 5n square and this is 6n square. So you are left with only n square here. See, from these three terms you just common out n square, right? If you common out n square, what will happen? I am rewriting here. See, s we need actually, right? And that s is nothing but n square times of n square plus 2n plus 1 divided by 4. And that simplification value is what? This is n plus 1 whole square again, right? That simplification value is n times of n plus 1 by 2 whole square. See, your final result is n times of n plus 1 by 2 whole square. Have a look at this. It's a complete simplification. For the space concern, I am adjusting here. Have a look at this. Okay. So initially we need to start with an identity. I already mentioned you many times. See, proofs are actually not mandatory for problem solving. But see, as a discussion, we need to learn how the rule is generated. So for that I mentioned here, right? At the end, you need to memorize the sum of the cubes of the first n naturals as just n plus 1 by 2 whole square. I will again write here after erasing this, right? Just have a look at this. The squares. And now with this complete discussion, we have the sum of the cubes like this. 1 cube plus 2 cube plus 3 cube plus and so on plus n cube is equals to n square of n plus 1 square by 4. We can rewrite it like n times of n plus 1 by 2 whole square also. Right? This is the sum of the squares of the first n cubes. This is the rule, right? The first n terms you need to consider. For example, if anybody asks you to find 1 cube plus 2 cube plus 3 cube plus and so on plus 10 cube. If they ask you to find the sum of the cubes of the first 10 naturals, how to find? Then automatically you can use the same formula for n is equals to 10. Then your answer is 10 into 10 plus 1 is 11 by 2 whole square. See, and if you simplify 2 5s and then 5 11s is 55. So this is equals to 55 square. Have a look at this. Sum of the cubes of the first 10 naturals is 55 square if you add, right? Without that complete time taking addition. See, this formula helps you to find the summation as 55 square directly, right? Like this, we can use these formulas to find the required summations. First of all, you need to keep in mind that sum of the first n naturals as n into n plus 1 by 2. Sum of the squares, sum of the cubes as n plus 1 by 2 square. For example, if I have a problem like this, I will give you one problem for you. See, for example, I have a problem like this. Something like 7 cube plus 14 cube plus 21 cube plus 28 cube plus and so on plus. See, something like what you have to say. Take some number like, we are considering all the 7 multiples. You may start at some 7 multiple. You may take it as some 98 cube, right? Some 7 multiple. I am starting there. See, what is the sum of the cubes of all these numbers? Look at this: 7 cube, 14 cube, 21 cube, 28 cube. See how to find the summation. You will rewrite this 7 as 7 into 1 cube. Is it right? And that 14 as 7 into 2 cube. Is it right? Right. And then the 21 as 7 into 3 cube. Right? Write everything. And if you continue like this, at the end that is 14, which is nothing but 7 times of the 14 cube. Is it right? Since it is 98, 7 14 is 98. So, if you look at this, every term contains 7 into 1 cube, 7 into 2 cube, 7 into 14 cube, like that. If you apply that cube for the two terms of the inner bracket, 7 cube 1 cube, 7 cube 2 cube, 7 cube 3 cube, 7 cube 14 cube, like that you will have. So if you pick out that 7 cube into, then you left with 1 cube plus 2 cube plus 3 cube plus and so on plus 14 cube. And this 7 cube is still remain there like that, 7 cube. And now if you look at this, see sum of the cubes of the first 14 naturals, right? 1 cube to 14 cube we have. See, starting from the 1 to the 14 with the cubes. And your answer is, what is your answer? n plus 1. So 14 times of 14 plus 1 by 2 to the power 2 square. So if you simplify this numerically, you will get this summation of 7 cube to the 98 cube. Have a look at this. See, basically we have few formulas for the sum of first n naturals, for the sum of the squares, for the sum of the cubes, and using all those formulae, we can find this type of problems. We can solve these type of problems, right? Have a look at this. I will move for the next thing. I am going to erase this. And the next thing is about summation operator. That means notation of sigma. Right? See, usually these summations are represented using the sigma notation, sigma operator. Right? See, we may call it as notation of sigma. See, sigma means usually we can use this symbol for this sigma notation. That symbol usually represents means summation. See, whose summation? So we need to make it like this. For example, sigma of, right? See, the sigma operator adds some values. See, which are following a particular rule. Sigma operator or sigma symbol adds sum ups, some values which are following a particular pattern. For example, if I mention you like this, sigma of some 3n, or otherwise you may take it as some n square initially, sigma of n square, or you may take it as k square, no problem, everything, right? See, initially I need to start sigma of k running from 1 to n k square. See, these type of situations you may face. Look at this. First of all, I am going to explain this. Sigma of k running from 1 to n square. K is equals to 1 to n square. Like that we need to read. How to read? Once again I am repeating. You need to read it like this. Sigma k running from 1 to n k square. How? Sigma k is running from 1 to n. And that particular rule is k square. Now, since sigma k running from 1 to n k square, you need to replace k with 1, 2, 3 up to n. Right? See, this is again, sometimes some may write it like this also. Sigma k is equals to 1, 2, 3 and so on n k square. Both are actually same. Here we mentioned it as k to 1 to n, and here 1, 2, 3 and so on n are mentioning, right? See, you need to take only natural values in the place of that particular variable where the sigma is running. Initially here I mentioned you it as k, right? Sigma k running from 1 to n, sigma 1, 2, 3 and so on k square, and this is nothing but you need to replace k with 1, then it becomes like 1 square. You need to replace k with 2, it becomes like 2 square. And you need to replace k with 3, it becomes like 3 square. And you need to replace k with n, at the end it becomes like n square. So sigma k running from 1 to n k square is this or this, both are same. This is the sum of the squares of first n naturals, is it right? So sum of the squares of first n naturals are also represented like this. See, you just don't concentrate on this variable. It may be k, it may be p, it may be t, it may be a, it may be n, all are same, is it right? See, for suppose if some people may mention it like this. How? See, instead of that sigma k running from 1 to n k square, they may write it like this. Sigma t running from 1 to n t square. What will happen? Nothing will happen, right? See, or otherwise you may take p in the place of t. Sigma p running from 1 to p square. What will happen? Everything are same, is it right? We need to replace that variable. Either it may be k, or it may be t, or it may be p. You need to replace that variable with the natural numbers starting from 1 to n, 1 by 1. And you need to add all those values since sigma is indicated, right? So all these are same to that 1 square plus 2 square plus 3 square plus n square. And some may write it like this also. Sigma n running from 1 to n square. See, actually it is not correct actually. Sigma n running from 1 to n square. See, you need to replace n with 1 to n again, and that variable is n. Because you need to take any variable in the place of k. So sometimes to confuse you, they may give you like this, or in sometimes they leave it like this. Sigma n square. Sigma n square means you need to add squares of the first n naturals. All are same actually. This is basically the meaning, the sense of this sigma operator. Once again I am repeating you. See the notation of sigma. How the sigma operator is helpful. How to understand the sigma operator. Sigma operator means basically summation, right? Whose summation? Sum of the values following this particular rule, right? Based on this rule, how you generated those values? By replacing the variable by the natural numbers from n to 1 to n. See, we have a rule and we have some natural value, starting value and the ending value. And by replacing those natural values one by one in that particular rule, you will get different values at the end. And after adding all those resultant values, the final summation is the sigma operator, right? Just have a look at this. I will give you a few more examples related to sigma. And at the end, what I am going to conclude you is, with all this discussion, you may write it like this. Sometimes in some cases you may find it like this. Sigma n square is nothing but sum of the squares of the first n naturals, and which is equals to n plus 1 to n plus 1 by 6. Is it right? All are same. Okay. So just you need to understand how the sigma operator is working. Just have a look at this and I will give you a few more examples. Yeah, is it right? Can I erase this? So, sigma operator, how it works? It sums up certain values which are following a particular rule, right? And now for example I have, see, like this. Sigma k is equals to 1 to n, have a look at this. 3k plus 4, what will happen? Just have a look at this. Sigma k is equals to 1 to n 3k plus 4. See what it means, right? You need to replace k with 1 once, k with 2, k with 3 like that, and all those values you need to add up. So this is equals to, if you replace k with 1, 3 into 1 plus 4. Okay, first value, plus second value is 3 into 2 plus 4. Third value, 3 into 3 plus 4. And then at the end, the nth value, 3 into n plus 4. Is it right? You need to replace k with the natural numbers from 1 to n. And now if you look at all these things again, see 3 into 1, 3 into 2, 3 into 3, 3 into n. From all these things you have a chance to common out 3. So you get it as 3 times the 1 plus 2 plus and so on n. Plus, have a look at this, n force, because k is running from 1 to n, there exist n terms, so you need to add 4 for n times and your answer is 4n. And now this is equals to 3 times of 1 plus 2 plus and so on, n is nothing but n into n plus 1 by 2 plus 4n. If you simplify this, you will get this answer, sum of the n terms which are in the form 3k plus 4, right? Is it clear? And see, instead of moving with all this procedure, we have another chance to simplify it. How? This is equals to, I may rewrite it like this, because it is sigma, here also the sum, sigma means sum, so we have a chance to split the sum. So split it like this, sigma 3k plus sigma 4, because sigma is sum, here it is again plus, so I split it like this, sigma of 3k plus sigma of 4. Then how it becomes? See, sigma of 3k, see I won't mention the k, see the k is changing from 1 to n, since k is changing, 3 is not affected by that k. So you may write it like this, this is equals to 3 times of sigma k plus, here only 4 is there, but that 4 is also not affected by that k, you may write it like this, 4 times of sigma 1. And now this is equals to 3 times of sigma k, k is nothing but a linear term, 1, 2, 3 like that you need to take in the place of k. And if you add all those n, your value is n times of n plus 1 by 2 plus 4 times of sigma 1. See how many ones you need to take. See, this is actually sigma k running from 1 to n 1. So sigma k running from 1 to n again is nothing but n only, no? That is 4n. Just have a look at this. See, this is the complete simplification. This is the direct simplification. Both the answers are same. I mentioned you both. Is it clear? Just have a look at this. How to use the sigma operator in finding the sum of the first n different terms. Have a look at this. I mentioned you 4 different sigma summations on the board. Sigma k running from 1 to n1, sigma k running from 1 to n k, k square like that. See, it is very clear that we are going to add what? We are going to add 1 for how many times? N times. Since k is running from 1 to n, right? Since we are adding 1 for n times, its summation value is n. Okay. K. What are the values of k? 1, 2, 3, 4 up to n. K is 1. You need to take 1 because the rule is 1. K is 2. Again you need to take 1 only. K is 3. Again you need to take 1 only. Like that it changes, right? If you feel any confusion related to this one, or otherwise you may take instead of 1 any other number. For example, sigma k is equals to 1 to n, you may take it as 7. Right? See, if k is equals to 1, consider 7. K is equals to 2, consider 7. K is equals to 3, consider 7. K is equals to n, consider 7. How many 7s you need to consider? N 7s. If you add all those things, what will happen? Your answer is 7n. If it is 1, 1n. If it is 10, 10n. Like that. Sigma k running from 1 to n k. See, replace k with 1 to n like that. Then the summation is sum of the first n natural numbers n plus 1 by 2. And it can be, this summation is the sum of the squares n plus 1, 2n plus 1 by 6. And this is sum of the cubes. It can be written as n plus 1 by 2 square. Just have a look at this. Okay. See, once again I am rewriting for you. This sigma k running from 1 to n 7 is nothing but 7 plus 7 plus 7 plus and so on plus 7 for n times. And here this is nothing but 1 plus 2 plus and so on plus n. And here it is nothing but 1 square plus 2 square plus and so on plus n square. And this is nothing but 1 cube plus 2 cube plus and so on plus n cube. Is it clear? I think everything is clear there. And not only like this, see, by regulating that k also, sometimes they may write you like this. right? See, sigma k running from 1 to n 7. Sometimes they may write it like sigma 7. Sometimes they write the sum of the first n naturals as sigma n, and the sum of the squares of the first n naturals as sigma n square, and the sum of the cubes of the first n naturals as sigma n cube. And this is basically the way of expressing these sum rules using sigma operator. Have a look and go with the screenshot right now. If you have any doubts, just raise your hands. Right, we need to find the sum of the n terms which are on the form 3 square, 7 square, 11 square, 15 square and so on. First of all, to solve these type of problems, right, you need to find out the general term of the terms involved in the sequence. So first of all, my check is the numbers involved in this problem are 3, 7, 11, 15 and so on. If you look at this, all these numbers 3, 7, 11, 15 and so on are forming an arithmetic sequence with the first term 3 and the common difference 4. Is it right? Since they are forming an arithmetic sequence, then its nth term is given by the rule that a plus the first term 3 plus n minus 1 times of the d is nothing but the common difference. What is the common difference here? It is 4. So 4. Then this is equals to, you get it as 4n minus 1. Is it right? 4n minus 1 is the nth term. Clearly it is right. Why? If you replace n is equals to 1, you get 3 square. N is equals to 2, you get 7 square. N is equals to 3, 11 square. So with that idea, since the nth term is 4n plus 1, the required sum what we are going to find is equals to sigma k running from 1 to n 4k minus 1 square. I have a chance to write it in this manner. Just have a look at this whether it is right or wrong. 100% it is right, because sigma is going to add different values which are following the rule 4k minus 1 whole square. But the k is running over 1 to n. If you take k as 1, you get that as 3 square. So your first value is 3 square. If you replace k with 2, 7 square. The second value is 7 square. If you replace k with 3, 11 square. The third value is 11 square. So likewise you have different values 3 square, 7 square, 11 square and then up to n square. And we are going to add all those. So that's why I am utilizing this sigma operator. Now you have to find sum of these values is nothing but finding this sigma of 4k minus 1 whole square. Now try to find this. Since it involves with 4k minus 1 whole square, just apply that. 4k minus 1 whole square. Sigma k running from 1 to n, 4k minus 1 whole square is nothing but 16k square minus 8k plus 1. Is it right or wrong? Just I am applying a minus b whole square formula. 16k square minus 8k plus 1. As I mentioned you, since sigma is sigma operator, we have a chance to split the summations using the sigma. So just try to split it. It becomes like sigma 16k square minus sigma 8k plus sigma 1. Since sigma is the summation operator, you need to split with plus or minus signs. But you have no chance to split with the multiplication and division, right? So you have no chance to write it like sigma 16 into sigma k square, right? See, don't write sigma a into sigma b as sigma ab. This is a wrong task actually. But if you have that sigma of a plus b, then you have a chance to write it like sigma a plus sigma b. Have a look at this. See, sigma splits the plus sign. It won't splits the multiplication sign, right? So now here I am applying that sigma now. See, and now again this is sigma 16k square. See, actually you need to feel the sense every time. Since 16k square means what? 16 into 1 square plus 16 into 2 square plus 16 into 3 square plus like that up to 16 into n square. See, that means 16 is common for all the things. So just take it out that 16. Then how it becomes? Then in the next step it becomes in such a manner. This is equals to 16 times of sigma k square minus 8 is also not involved by that k, so keep it out, pick it out. See, 8 times of sigma k plus sigma 1. Now we have different formulas. Sigma k square. See, actually that sigma k square or sigma n square where the k is running over 1 to n, so you need to apply sum of the squares of first n naturals as n into n plus 1 into 2n plus 1 by 6 minus 8 times of sigma k n into n plus 1 by 2 plus sigma 1 is n. Now if you simplify this, you will get a result in terms of n. That result, that summation in terms of n represents the sum of n terms of this particular sequence. Have a look at this problem. See, like the previous problem, to solve this, first of all you need to find the general term of the sequence. See, to find the general term, your first observation is, look at this 1, 7, 5, 9 and then 13 and then 17 like that. 1, 5, 9, 30 and 17. All these are the first terms of that sequence, and whereas coming to the second terms, what we have? 4, 7, 10, 13, 16 like that. Still there are many, right? See, this is one arithmetic progression, right? And this is another arithmetic progression. Both are two different arithmetic sequences. For the first arithmetic sequence, the first term is 1 and the common difference is 4. And for the second one, first term is 4 and the common difference is 3. If you find nth term for this arithmetic sequence, 1 plus n minus 1 into 4 will give us 4n minus 3. Whereas for the second arithmetic sequence, the first term is 4 plus n minus 1 into the common difference is 3, right? So, and if you simplify, you will get it like 3n plus 1. Just have a look at this. See, that is 4n minus 3, this is 3n plus 1. The general terms. So, the last term is 4n minus 3 times of 3n plus 1. Now, in this case, to find the summation, I will write it like this. Sigma k running from 1 to n, you just take them in k form. 4k minus 3 into 3k plus 1. Have a look at this. See, product of these two with the sigma operator, where k running from 1 to n. Replace k with 1. What you get? 4 into 1 minus 3 is 1. 3 into 1 plus 1 is 4. Replace k with 2. You will get the second term. Replace k with 3. You will get third term. So this sigma summation is equal to the given sum. Now for this, what we have to do? This is equals to sigma. You just multiply these two. 4k and 3k is 12k square. Plus 4k and minus 9k is minus 5k minus 3. Just have a look at this. 4k into 3k is 12k square plus 4k minus 9k minus 5k and minus 3. And